Hello, Marvelous Algebra 1 students, and welcome back to Topic 7. We are on Lesson 7.4 today, which are going to be properties of square roots and reducing square roots. To open up today's lesson, I have three problems for you. Problem 1, Problem 2, Problem 3, with some multiple choice answers, or maybe I should even say multiple select, because there are certain problems where you'll have to pick more than one answer. So I'd like you to think about these three, and you'll notice on here that there's a spot where I checked my answers without a calculator by, and then using a calculator by. So why don't you guys try each of these, see what you can do, see if you come up with the right answers, and then we'll go through some of them. We won't go through all of them because you should know how to do hopefully the first two, but we'll definitely focus in on that third. So take a few minutes. Once you've tried them, unpause. We'll see how you did. Ready, set, go. Alright, well, you're back. Hopefully you did okay with these. If you saw 5 over 10, I bet pretty instinctively you already picked D, and you'd be correct there. But you'd also be correct by picking A, right? 18 is half of 36, 5 is half of 10, 1 is half of 2. The others are not correct, right? 5 tenths, 18, 36, and 1 half are all half. They're less than 1. The numerator is smaller than the denominator, and that takes out B and C. Now, how could you check your answers here? There's a few options. Without a calculator, you could have gone through and divided these out. You could have gotten common denominators, whatever sounds good to you. With a calculator that I will quickly focus on, we should be able to go through here and turn on our calculators, and you should be able to turn your answers into decimals, right? You could do 5 divided by 10. You'd get a decimal there, 0.5. Okay. And then you try 18 over 36. Whoops. There we go. And you get 0.5. And you're like, oh, the decimals match. That means that they are the same answer, just a different form, a different way to represent it. Okay? Nothing bad. Well, what if you moved into 2? Well, 2 has a couple tricky things on here as well. 7/4 is the same as 1 3/4. It is not the same as 7 1/4. It is the same as 1.75, and it is not the same as 21 over 12. Or is it the same? I'm not sure. And so if you're not sure, you have a couple options. Multiplying by 3 would tell you, oh wait, it is the same as 21 over 12. It's a weird way to represent that. But the other way, of course, is using a calculator. So we could try those again. We'll see if I can remember this. We have 7 over 4. 1.75. So that already shows the decimal. We could do 21 divided by 12, 1.75. And then the last one is weird. And this fraction notation, even though it kind of makes sense to read to us because we're used to it, is actually really bad notation in math. We really don't like this notation because the notation 1 3/4, you write it as 1 and then there's like a space and then 3/4, right? It looks like 13/4 there too, which isn't great. You might be tempted to say, oh, well, 1 3/4 are right next to each other. So doesn't that mean, and I'm just going to insert a multiplication sign, doesn't that mean 1 times 3/4? Because everything else in math, when you have a number right next to something else, whether it's another number, a variable, it means multiply. But if you multiply those, you get 0.75. Strangely, that 1 3/4 notation actually means 1 plus 3/4 more. And that's where the 1.75 comes from. Yeah, it's an invisible plus sign. Bet you didn't see that coming. All right, on to the last one. Well, for this last one, this square root of 72, we've seen square roots before, but nothing quite like this, right? We've seen square roots where I said, what's the square root of 36? And you'd say, oh, the square root of 36 is 6 because we know there's that invisible 2 hiding for the index. So because 2 of those 6s multiplying gives you 36. Easy enough. But the square root of 72 is tough because it's certainly not 8. Because 8 times 8 is 64. That's too small. It doesn't match the radicand of 72. And it's also not 9, because 9 times 9 is 81. Right? 72 is somewhere in between 64 and 81, which means the answer to the square root of 72 is somewhere in between 8 and 9. 8.1, 8.2, 8.5, I'm not quite sure. And so we run across a style of square root we haven't dealt with before because 72 is not a perfect square. There is an answer to the square root of 72. We just don't know it. And to make matters even trickier, none of these numbers down below give us a good indication of what the right answer is. None of them are decimals, and it seems weird that 3 and 8 would be 72 or 6 and 2. This 12 and 6 seems like, 12 times 6 is 72. There's some basic multiplication. My guess, though, is if you have a number right next to a root, it does mean multiply, unlike that weird plus thing up here, right? This does mean multiplies. We would read this as 3 times the square root of 8. Well, what's the other way we could check to see if these are actually the right answers? We'll use our calculator, right? Let's go through and let's check the square root of 72 first. So the square root of 72 as a decimal is 8.485281374. Now, this decimal stops here, but that isn't actually the final answer. Technically, this decimal goes on forever. It doesn't just have 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers past the decimal. It has an infinite number of numbers. There is actually no perfect fraction to write this decimal either. And in fact, if we were to take this decimal, and I'm just going to do squared, it'll take my answer and square it. We get back to 72. So that is the square root of 72 because 8.485 whatever times itself is 72. Okay, cool. So 8.485 is what we're looking for. Well, the first thing we saw was 3 times the square root of 8. There's that same decimal. So that 3 square roots of 8 is an answer. 6 square roots of 2 is next, okay? So let's try that one. So we have 6, and I don't even think I need to put the multiplication here. 6 square roots of 2. Oh, that's an answer as well. Well, that's exciting. Okay, these first two. Well, the third can't possibly be an answer. 2 square roots of 18. That looks so different. 2 square roots of 18. Ah, that's an answer as well. Might as well finish off the last one, the square root of 6. And I need to move my cursor out of there. And then the square root of 12. It might have been the other way around, but multiplication is commutative, associative, so you can do it in any order. They're actually all the same. So that's a little bit weird because we were certainly able to check our answers using a calculator. However, how would you have known that square root of 72 matched all those without a calculator? And actually, that's what we're going to investigate today. So let's get to our new stuff, and to get to our new stuff, we need a bit of review first. We'll start with square roots. A square root, or any radical or root, remember radical is just that symbol right here, right? A square root is a type of radical, has 2 possible answers, right? So, a perfect square, what are some examples of perfect squares? Do you remember? Right? A perfect square could be something like 9 or 25 or 49. Those are all perfect squares because when you apply a square root to each of those, you get what? Well, you get what we call integers. We get nice numbers, no decimals. And there's a very limited number of perfect squares. Technically, there's an infinite number of perfect squares, but there are arguably fewer perfect squares than there are non-perfect squares, right? However, when you take the square root of any other number that's not a perfect square, the answer is, and this is a fun word, irrational. Okay? Which means you cannot write that answer as a fraction of 2 nice numbers. You actually know one other irrational number. You learned it in middle school. That's right, your irrational number is pi. We approximate pi as 3.14, but if you ever did those pi memorizing contests, I was always about the pi eating contest, not the memorizing, but you might know it's 3.14, 159, so on and so forth, forever. Right? Now, unless we have to, it's actually considered a no-no to write the decimal version of a square root because the decimal version isn't perfectly accurate. Right? Instead, we just leave the answer as a square root. For example, if the answer to a problem was the square root of 72, we would just box the square root of 72. We wouldn't actually turn it into 8.485 whatever, because eventually you have to stop writing decimals, right? But wait, In the opener, we saw the square root of 72 was equal to a whole bunch of things. It was equal to 3 square roots of 8, 6 square roots of 2, 2 square roots of 18, and even the square root of 12 times the square root of 6. So if there are 5 possible answers, including the square root of 72, is there one that we prefer to write? Well, think back to fractions, right? We had this fraction 5/10 up here. Between 5/10, 18/36, and 1/2, is there an answer your teacher might prefer? So in order to answer the question of A, is one of these 5 answers better than the other, and B, how do we get to those 5 answers, we're going to have to go back to some properties of square roots first. Each of these properties below are always going to be true about square roots. So let's start easy. Number 1, to add square roots together, the radicands, oops, I started to put an extra S there, must be the same. However, the radicand never changes. The coefficient, remember the coefficient is the number in front that counts the number of radicals you have. So, 2 examples. We have 3 of these square roots of 2, and we are gaining 10 more of these square roots of 2. So the question this is asking us then is how many square roots of 2 do we have? Well, if you have 3 plus 10 more, that means you have 13 square roots of 2. That's as far as we're going to go. You could type that into a calculator, 13 times the square root of 2, and get a decimal, but we don't like those icky decimals. We want to keep it nice and succinct, nice and easy and short. All right, let's look at the next one. 8 square roots of 5 plus 3 square roots of 5 minus a square root of 5 plus a square root of 6. Well, let's deal with the square root of 5s first. 8 square roots of 5 plus 3 square roots of 5 minus, you guessed it, an invisible 1 square root of 5. So I'm just going to do this in 2 parts. 8 square roots of 5 plus 3 square roots of 5. 8 plus 3 is 11 square roots of 5. There is still a minus 1 square root of 5 and plus a square root of 6. 11 square roots of 5 minus 1 is 10 square roots of 5. This square root of 6, though, does not have a like radicand with the 5s, and so just stays with it. And so our final answer is 10 square roots of 5 plus a square root of 6. All right, let's move on. You can multiply square roots with any numbers as the radicand. They do not need to match. That is why the square root of 12 times the square root of 6 is the square root of 72. 12 times 6 is 72. 3 times 6 times 2 we'll do in 2 parts. 3 times 6 is 18. There's still a square root of 2 though. And 18 times the square root of 2 is the square root of 36. Well, actually, the square root of 36 is just 6, isn't it? We might as well keep simplifying from there. And that brings us to our next one, because a square root times itself equals the radicand. And here's a big reveal: without the square root. So, square root of 5 times the square root of 5 is the square root of 25. But what is the square root of 25? Oh, that's right, it's 5. And so in fact, if you had the square root of 5 times itself, a lot of people would just skip right to the answer and say that's 5. For example, I don't know what the square root of 27 times the square root of 27 is with a square root. 27 times 27, it's a big number. It's more than 400, I don't know. But I do know the final answer is just 27, because a square root times itself just gives us the number on the inside, the radicand. And in fact, that leads us to one other discovery. A number times itself can of course be written as that number squared. And as a square root looks for a number times itself, we say that a square root cancels out a square. The square root of 3 squared. Well, do the 3 squared first, that's 9. And then the square root of 9 is 3. So a lot of people would say the square root of 3 squared, they would cancel the square root and the square and just say that's 3. Same thing, the square root of 8 squared, I don't know what the square root of 8 is, but I know if you have a square and a square root, they cancel, and we'll just leave you with the 8 on the inside, right? And the reason why here actually I can just do it a second time, is if you have the square root of 8 squared, that means do the square root of 8 times itself. That's what a square means. But we just learned up above that when you have a square root times itself, it's just the number on the inside. And so that's why we say the square root of something squared is just the number inside. All right, let's look at 5. Try to take the square root of negative 16 on your calculator. What happens and why? We'll give it a shot. I'll do it too. But you guys should be trying on yours. So we have the calculator turning on. There we go. The square root of negative 16. Non-real ANS. Well, that's weird. I might as well write that over here. So our calculator said the square root of negative 16 is a non-real ANS. I bet we can finish that off with the answer. Non-real answer. Huh. Well, that is because the square root of a negative number is not a real number. Do you see why? Well, let's say that you thought the square root of 16 was negative 4. I'll put a little question mark. Well, then we try negative 4 times itself to check our work, but a negative times a negative is a positive. 4 times 4 is 16, and 16 is not equal to negative 16. Some students say, well, couldn't the square root of negative 16 equals negative 4 and 4? No, a square root can only give you a number times itself. These are two different numbers, so we can't do something like that. Well, we actually say the square root of 16 has no real solution. Sometimes in Algebra 1, you'll hear people say that square root of 16 has no solution. That's not quite accurate. When you get into Algebra 2, you'll learn that the square root of 16 does have solutions. They're just not real. What's the opposite of real? Imaginary? Are they imaginary? Well, something to think about for the next year or so. Your calculator will sometimes say domain error because you are not allowed to substitute in negative 16 into a square root. All right, now that we have a better understanding as to how square roots work and some different properties that work with them, let's discuss simplifying square roots. Now in math, we do want to make it easy to check everyone's answers. That's why we reduce fractions, and the same idea applies to simplifying radicals, or you could say roots here if you wanted. A square root is fully reduced when there are no perfect squares left inside the radical. I will tell you before we jump on to the next part, there was another reason that people used to reduce square roots. That was before calculators though, and the idea was you wanted to make, and we'll take a look back on this first page, you wanted to make the number inside the square root as small as possible. So as we look at these options here, there's an 8 inside, a 2 inside, an 18, and a 12 and a 6. The one that has the number small as possible is B. So out of all of these answers, B is probably the best. And the reason why is because you could get a more accurate answer with this smaller square root than you could with bigger ones, right? They kept really accurate ones here, and they could do some quick calculations. The larger the square root, the more obnoxious it became. We have calculators now, though, so that's not really too much of a point anymore. Okay, now at this time, your teacher should be passing out a double-sided list of the integer factors of every number from 1 to 100. You are really going to want to hold on to this page. It's going to help you a little bit in this unit, but so much in the next unit when we start to factor. So the sheet should look something like this. Factors 1 to 100. Definitely put your name on it. Now, you'll notice as you go through, let's just pick a number like, 32. If I pick 32 in here, they gave you 1 times 32, 2 times 16, and 4 times 8. That means that 32 has 6 factors. 1 goes into 32, 32 goes into 32, 2, 16, 4, and 8. Some students say, well, what about 8 times 4? Well, sure, and also 16 times 2, and also 32 times 1, but we already used those. I'm not going to double count the factors here. So we have unique numbers that go into the bold number at the front. Additionally, we have a whole bunch of boxed numbers up here. We might even say numbers with squares around them. And at the bottom it says any number in a box, any number in a square is a perfect square. And can you see why? 49 is a perfect square. 7 times 7. 5 times 5. Right? If you were to take the square root of 36, where is it? Up, the square root of 36 is 6. 6 times 6 is 36. So this lists all the factors of every number from 1 to 100. You really, really, really need to save this page. It's going to save you next topic, but also for this one. Okay, let's begin. We're going to do the first few problems twice. And we're going to do that because I'm going to give you two different ways to get to the answer. The first way is the way that I do them, but my multiplication facts are pretty good even without that factor sheet, and so this way tends to be faster for me. However, the second way is going to be a foolproof way to go through and break down the numbers, especially with that factor sheet. And so you might like the second one a little bit more. It's slower, but it'll absolutely get you there. So here we go. The first thing we're going to do is work with the square root of 72. And we are going to first find a perfect square that goes into 72. Now, I already know a bunch of perfect squares that go in here. I can kind of hold them in my head really quickly. We know they need to be smaller than 72. And so, kind of going the slow way, I'm going to jump back to my list of perfect squares and think about ones that go into 72. I know 1's going to go into 72. I'm pretty sure 4 is as well, and I'll check these in a bit. I think 9 is going to. Okay, I'm not sure about 16. 25's not, though. 72 doesn't end in a 5. And I wouldn't write on your sheet like this because you'll need this. 36 might. We'll check that one. And 49, I'm pretty sure, is too big. All right, and then same thing, 64 is too big as well. So remembering those numbers, jumping back to 72, let's look at all the numbers in 72 and think, are any of these perfect squares? Well, we discussed 36 is a perfect square, 4 is a perfect square, and 9 is a perfect square. So there are 3 perfect squares in 72. So sometimes students will say, well, wait, which perfect square are we going to use? And the answer is whatever you would like. I'll start with the largest perfect square, 2 and 36. So I'm going to break down or factor out the square root of 72. I'm going to write this, and I'm actually going to do this one 3 times over here. So I'm going to take the square root of 72 and say, okay, I looked at the square root of 72. I found a factor pair that contains a perfect square. I saw that 36 times 2 still makes 72. So I've written nothing false here. The square root of 72 is still the square root of 36 times 2. Easy. Then we're going to use a fact, and I'm going to jump all the way back up over here, that when we had 2 numbers in separate square roots, they became together. Same thing over here. 3 times 6 is 18, and so we're just going to manipulate that just slightly. The square root of 36 times 2 is certainly the same as the square root of 36 times the square root of 2. 36 and 2 gives you 72. Then we're actually going to use the square root, because using square roots, applying a square root to a perfect square, is pretty darn nice. The square root of 36 we know is 6. Square root of 2 doesn't have a square root. Or it does have a square root, that's a lie. It just has a decimal and a rational square root, and so we're not going to do that. Now, are we done? Well, let's go back to 2 and think, are there any other perfect squares in 2 that we can divide out or square root out? So going all the way back to 2 here. Here is 2. Are either of the numbers that go into 2 a perfect square? Well, 1 is a perfect square. So are we going to use that? Well, don't write this part. I'm actually going to erase it. We could do the same thing. We could say this is 6, and then 2 is 2 times 1. And that becomes the square root of 2 times the square root of 1. But what is the square root of 1? The square root of 1 is just 1, and 6 times 1 is 6. And so we end back up with 6 square roots of 2, which is the same thing we got here. So if the only perfect square left in there is 1, you're done. We don't actually factor out the 1 or apply the square root to a 1 because nothing changes. Now, I said I'd do this problem 3 times, and I try not to lie to you too much. So let's see why. Well, for this one, I picked out the largest perfect square, which is usually good advice. The largest perfect square will simplify down the fastest. But let's say you didn't spot that, or you were doing mental math and you didn't realize 36 goes in there. You're like, nah, I remember 9. 9's a good perfect square. So you go, okay, I know I can rewrite 72 as the square root of 9 times 8. 9 times 8 is 72. We saw that on our factor sheet. And then I'm going to split this square root of 9 times the square root of 8. And then we know the square root of 9. The square root of 9 is 3. 3 square roots of 8. Ha! I'm done. But are you? We still need to go and look at 8 and see if there are any other perfect squares in 8. And you should be thinking multiplication in your head. What times what is 8? Well, there are a couple perfect squares that go into 8. There's 1 and 4. Now we know 1 isn't going to be useful, but 4 is. So I'm going to rewrite 8 as 4 times 2. Okay, so jumping back down here, we're going to go ahead and say 8 is the same as 4 times 2. And then we have square root of 4 times the square root of 2. What is the square root of 4? Oh, that's 2. And what is 3 times 2? That's right, that's 6. That should match the same answer there. So long story short, too late, we were breaking these down, and it actually doesn't matter which perfect square you pick. The only difference is that the larger the perfect square, the less work you're going to have to do. Let's try one more. There was another perfect square that went into 72, and I believe that was 4 times 18 is 72. I'm going to skip this step where I split it because I think you can understand what's going to happen here. The square root of 4 is 2, but there's still 18. Is there a perfect square that goes into 18? Yep. Isn't the 18 9 times 2? 9 is a perfect square. And what is 2 times 3? That is 6. So we did this 3 different ways and came up with the same answer. Do you see that factor sheet might be a little useful for you if your multiplication facts are a little shaky? Now, I did promise you a second way to do this, and this is a very common way to be taught to Algebra 1 students, and so your teacher will probably have some sort of fun story to explain this, and I'll leave that up to them. But we're going to go through and do something similar to what I did over there, but instead of rewriting the problem every time, I'm going to use a factor tree. And the way a factor tree works is we go through and we make a branch with 2 endings here. And what we're going to do is figure out a way to divide 72. Now, the nice part is with your factor sheet over here, you can take that 72 and say, well, we actually have, what is this, 6 different possibilities. 1, 2, 3, 4, 5, 6. I don't want to use 1 in 72. We never want to use 1. So we really have 5 possibilities. Let's use one we haven't used yet, though. So I'll use 3 and 24. Neither of those are perfect squares. So 3 times 24. I've broken down 72, so we want to make sure to cross that out. And we're crossing it out because we don't want to get that number confused for what we're about to do later on. All right, we're not done yet because our goal here with this factor tree is to break down every number as far as possible, but no ones. So for example, 3 in our set of factors only has 1 times 3. I'm not going to break this down into 1 times 3. Anytime a 1 comes along, it's not going to change anything. We're not going to do it. But 24, we can break down. What does 24 break down into? Well, there's a lot of different opportunities. 6 and 4, 8 and 3, whatever sounds good. I'm going to pick 8 and 3, though. So 8 times 3 is 24. Could have done 12 and 2. Notice I also crossed off the 24 because I broke that down. 3 we can't break down further, but we can break down 8 into 4 and 2. And we can break 4 down into 2 and 2. Now, There is a long way to do this and a short way, and I will show you both. I'm going to do the long way over on this far right side, though, just so you understand why this works, and then I'll do the short way, the way that pretty much everyone does in this space over here that I'd recommend you do. So, long way first. We are going to take that square root of 72, and we are going to rewrite it. We're going to rewrite it using all of the uncrossed out numbers from greatest to least. So I had a 3, a 3, a 2, a 2, and a 2. Then we're going to take any squares and rewrite them. So 3 times 3, this guy right here, we can write that as 3 squared. 2 times 2, I can write that as 2 squared. This little loner 2 at the end is just hanging out like, hey guys, how come you guys all got friends? Now, there's at least one student in every class every year that's very astute, and they say, well, wait, couldn't you have written these 3 2's as 2 cubed? Yep, you're right. There's a reason, though, that I didn't do that. The reason that I didn't do that is because when I split this, and we are going to split this again, into individual square roots, we need to remember something about a square root and a square from the previous page. What happens when you have a square root and a square? Oh, that's right. We say that they cancel each other out. So what's going to happen here is we are just left with a 3, no square root of square, just left with a 2, and then this guy doesn't have anything to cancel, so it stays with the 2. A square root does not cancel a cube or a fourth power or anything like that. It only cancels a square. So we try to make as many squares as possible. Then 3 times 2 is 6. Square root of 2. Now, I said that there was a short way and a long way, and this was the long way. This way makes, I think, mathematical sense. It's not a bad way to go. However, it's always awesome if you can draw a shortcut out of an algorithm or out of a pattern. And so here's our shortcut. You might notice that I had a pair of 3's, a pair of 2's, and a singleton 2. Well, our shortcut is anytime you see a pair, those numbers, only one of them gets written on the outside of the square root. Inside the square root, though, you get any of those singletons. I'm going to need to rearrange where my arrows are going here. There we go, and this singleton goes way over here. So anytime you have those doubles, those pairs, they go on the outside. Those loner numbers go on the inside. And this is the part where your teacher will have really cool stories. They may talk about numbers breaking out of jail, but one of them gets caught. And that's why when the 2 people break out of jail, there's only one number here. Or sometimes you'll hear teachers say, oh, this is a pair of friends, and friends get to play outside, but this loner stays inside. He has no friends, or whichever way you go with it. At its core, though, you should realize that these 2 3's are becoming a single 3 because we write them as a square, and the square root cancels the square, and so we just have a single 3 left over. However, if you want to remember this shortcut, anytime you have pairs, they go outside, and the singletons go inside, and then you can just simplify from there. That's a pretty quick method, right? You break down the numbers as far as you can, pairs outside, single numbers inside. Well, knowing that then, why don't you guys go ahead and try these next couple problems? There are really 4 more problems, right? 1, 2, 3, 4 problems. I would like you please to try the first 2 problems using both methods. You don't have to do it 3 times, but one method where you identify perfect squares and one method where you use the tree. And the reason I'm asking you to try them both is because you can't pick a favorite method just having used a method one time each. It doesn't work that way. You need to really understand the intricacies of each method before you make that decision. So go ahead, try each of those. Once you're done, mosey on back here. We'll run through it, see how you did, and get you going. Ready, set, go. All right. Hopefully you guys had some success here. Let's talk about how I do this. So 128. You'll notice that I chose a number that's not in your factor list. Oh, that's rude. How do we do that? And the answer is take some perfect squares and try dividing them out. So you should be pretty comfortable with a list of at least a few perfect squares. 4, 9, 16, 25, 36, 49. Those ones aren't too bad. You might even go larger than that, but 4 is a pretty common one. And in fact, one of our division rules we should know is that if the last two numbers are divisible by 4, and 4 does go into 28 7 times, then the whole number is divisible by 4. So let's divide 4 into 128. You can use your calculator if you'd like, but you'd find this multiplication isn't, or this division is not too terrible. 4 times what is 128? Well, 4 goes into 12 3 times, and 4 goes into 8 twice. If everything goes in nicely, you can do the division just like that. All right, now, looking at this, we're going to use another secret, sneaky method here. I bet 32 has another perfect square hiding in there as well. I, in fact, know that 4 times 8 is 32, right? 4 is still a perfect square. 4 times 8 is 32. And, in fact, I know that 8 has another perfect square hiding inside of it. 8 is 4 times 2. All right, simplifying this down, let's do the square root of each of the perfect squares. The square root of 4 is 2. The square root of 4 is 2. The square root of 4 is 2. The square root of 2 doesn't have a nice square root. It's not a perfect square. And we finish off by multiplying. 2 times 2 is 4, times a third 2 is 8, and so our final answer is 8 square roots of 2. I tried to do a square root instead of a box. Now, could you have done this faster? Certainly. You could have taken all of these perfect squares and multiplied them together. 4 times 4 is 16, a third 4 is 64, and that would actually tell you that 64 times 2 is 128, square root of 64 is 8, 8 square roots of 2. So if you'd known 64 is a perfect square, that's actually the next one on the list, and that it went into the square root of 128, you could have done this faster. So again, knowing your multiplication, a big step ahead in reducing square roots. All right, let's try that tree method. Ready? So we're going to go through and we're going to say, okay, what goes into 128? And we already did 4, didn't we? But let's say you don't even know 4. I know that it ends in an even number. I know that 2 has got to go in there. 2 times what? Well, maybe you turn to your calculator and you say, ooh, we're at 128. Should probably turn our calculators on. Third try's the charm. Fourth try. There we go. 128, and we're dividing it by 2. That's 64. Okay, so we get 64, cross out 128. 2 doesn't break down any further. 64 does, though. 64, what does that break down to? I bet most of us know that 8 times 8 is 64. Okay, and then we're going to come back to this because that's an important step, but I'm going to break down the 8s. 4 and 2, 2 times 2. Same thing here. 4 times 2, 2 and 2. All right, so then we say the square root of 128 equals, and let's use our shortcut, pair of 2's, pair of 2's, pair of 2's. Outside, outside, outside. 2 times 2 times 2, and we have this little loner 2 over there. A lot of times my students will forget the 2 at the very beginning, and they're like, what, there's nothing left? And that does happen sometimes. Well, then 2 times 2 times 2 is 8, and the square root of 2 stays. Now, you could have done this even faster, because what happens, again with this shortcut, I'm going to erase this temporarily, I'll put it back there in a second, is that if you get down to, these are called prime numbers, by the way, if they don't have any factors underneath them. If you get down to a prime number and then a pair, you can actually stop here, because this prime number is going to stay inside the square root, and this pair is going to go to the outside, and then you have no numbers left. And doesn't that match our answer on the other side? It seems a little bit quicker too. Just a trick to look for. Alright, let's try some smaller ones. These guys are actually in our factor tree, so let's make sure we can do them. 24, I'm just going to take a little peek at 24 up here. What's going on? So any perfect squares that I can see? No, no, no. Ah, bingo. 4 is a perfect square. Always a good sign if there's only one perfect square. It's probably the only way it's going to break down. This is 6 times 4. The square root of 4 is 2. And we're done. Now, we should check the square root of 6. The fact, though, that there were no more perfect squares with 4 or with 24 tells me that 6 will not have any perfect squares, and it doesn't. Great. What about that factor tree method? Well, factor tree, let's say you'd picked 8 and 3 for this guy. 8 is 4 and 2. 4 is 2 and 2. Okay, we pick our pair that goes on the outside, but then look at this, these single ones, we have 2 of them on the insides, a 3 and a 2. So is that 32? Well, no, everything with square roots is just going to be multiplication here. I'll just work to the side. 2 stays on the outside, 3 times 2 is 6, and I believe that is exactly what we got over there. You see how this perfect square method a lot of times is faster, though? All right, 2 to go. You can do these any way you want. Because they end in a lot of zeros, though, I'm thinking 100 is a good way to go here, right? I think for this 500 here, I'm going to break that down into 100 times 5. Yeah? Because I know 100 is a perfect square. The square root of 100 is 10. 5 doesn't break down any further. We say 5 is prime. So that looks pretty good to me. All right, what about the square root of 1,000? Well, let's use that same trick. We know 100 times 10 is 1,000. The square root of 100 is 10. I don't know, does 10 have any perfect squares in it? We'll check that factor chart one more time. No perfect squares. Easy enough. So we're going to go through and say our final answer is 10 squared is a 10. All right. Well, to finish off today, if you have any extra time, your teacher is going to have you work through this sheet. You probably won't get through all of these, and you'll notice there's some pretty crazy big numbers here. But your job is to determine which ones match, right? Have we done any of these yet? I don't think we did any of these. I will tell you that 8 matches 2 root 2. How do you know that? Well, you break it down the same way you were doing before, right? Square root of 8, you could say that that is 4 times 2. And we know the square root of 4 is 2, so 2 root 2. Okay. So you're going to go through and work these guys, practicing one or both of the methods, either this perfect square method or the factor tree, and work this out. So chat with your teacher about it and get this practice in. You really need to be pretty proficient at reducing square roots from here on out. We're going to see this a little bit in every unit for the rest of the year. So practice it, ask questions, and don't lose your factor list. You're going to use it for all the rest of the units for this year. Promise. Thank you, as always, for hanging out with me. Hopefully you learned a little bit of math today, and I'm excited to have you back next class for lesson 7.5.